Hello, everyone. Dr. Vaughn again. I am, by request, going to make a hopefully short video about the Chapter 3 assignment, and in particular, this question number 6. So this is factorial experiment. They give you this data, and you can download it into Excel. I've already done that. But what they have here is both the means and the standard deviations. This isn't not, the two scores. It's a mean and a standard deviation in parentheses. And what they don't give you is there's 25 different subjects, and they don't give you the score for each of those 25 subjects. And frankly, the book didn't really do you a very good job in the practice activities anyway of telling you exactly how to do that with the Excel templates or using the minor or data analysis tool pack in particular. So, since they didn't show you how to do that in the data analysis tool pack, the only thing that would really be left to your disposal would be to actually apply the formulas. And you can go into your book, that very first link that doesn't have any activities in it gives you the links, the formulas. You got to scroll through. It's like on the second page of the factorial design chapter. And it has all these sigmas in it and like the SSA. You really need the SSA formulas. Once you get the sum of square formulas for factor A, factor B, and for the interaction and for the error, the rest of it you can use addition and subtraction and division in order to figure out the ANOVA table. But I did figure out a way in which we could kind of sort of use the data analysis tool pack to help us compute those sum of squares, and then kind of do the rest of the addition and subtraction and multiplication, because what gets put out to the Excel document is not really going to be accurate when you only have the single mean and not all of the individual scores that contribute to that. Something like SPSS would do a much better job of this than Excel for whatever reason. So I'm going to just jump right to it. Here's our problem statement. You can see that I'm most of the way through it. You can see the green check marks. I've done this a couple of times just to make sure that I'm getting these answers right. But let me show you how I'm arriving at these answers. All right, so up here in Excel, what I did was first I took this, using the book formulas. All right, so I took the data and I got rid of the standard deviations and I put it in here. And then I totaled it together by multiplying by 25. So there are 25 people here and there's 25 people here. That gave me a total. And then I could compute an average. And so I get the totals and the averages for each of these, X factors and Y factors, or A factors and B factors. And then you can get this grand overall average. And I can show you these formulas if you're really interested. And then I used the formula from the book to actually calculate the SSA using all the sigmas and the sums. There's only two parts to the sum, so I just wrote it as a plus instead of a sum formula. And I got the right answer. So this 0.45 is the right answer for SSA. But this was going to be very tedious because now I'd have to go back through and figure out, first of all, this was a lot of work to get this. And then I had to figure out which cells I needed to divide by which in order to come up with this. So then I went back to this other version of the problem that I already had. And I'll tell you what I did with this one. Right, so this is the same set of data. And now I took that low and moderate and naive declarative procedural, and I took just the data and I copied it 25 times. Because there's 25 subjects here. In essence, I'm pretending that they all had the same score. All 25 people had 1.13. They didn't really all have 1.13. That was the mean. But, if I average 25 copies of that, I'll get that same mean. So this was a way of kind of putting in some fake scores that the mean would turn out to be correct, but Excel's going to think of it as the 25 different things, and then I could use an ANOVA replicated design. So I have the low scores in here 25 times, and then they have the moderate scores in here 25 times. So after I did that, now I can go into Anova Two Factor with Replication, which is under the Data Analysis Tool Pack. Anova Two Factor with Replication. And under the input range, I started in this blank cell, and I clicked and dragged all the way through the bottom of the data. So that's B10 all the way down to E60. So that included the labels and this little blank cell up here in the corner. And then I put in 25 rows per sample and the alpha value of 0.05. And then I put the output range over here on the right, so in cell F12. So when I did that, I got my ANOVA table over here, but then these sum of squares were mostly correct. The top three were actually correct, but this fourth one was incorrect. So now I went back and I looked at the problem, and they tell you to assume that the total sum of squares is 327.5. So I actually put that 327.5 over here, and then subtracted to figure out that this number would have to be 246.78. These three were correct. This was 327.50, and then I subtracted to figure out this number, and then I just typed it over the top of everything else that I had here. Then I actually re-added these numbers together to get an accurate total. It's still 327.50, but it's got some extra decimals over here because of the extra decimals that are up in the sample, the columns, and the interaction. The next thing that I did was I fixed the degrees of freedom here. So these degrees of freedom turned out to be correct, 1, 2, and 2. I knew that this had to be 149 because there's 150 data items. There's 25 in each of these, 75, 75, 70, 25, 25, 25, 25, 25, 25, 150 total. So the total degrees of freedom had to be 149. And again, you can use subtraction to go back and figure out that this number had to be 144. Right? So I just typed that number in. Now, the mean squares is always going to be this sum of squares divided by the degrees of freedom. So this one I just, can divide. This one you just divide. This one you just divide. And then I can type in those numbers over here. And actually, I think these were all correct because these numbers turned out to be correct. And so these numbers were already correct. This one, however, what I needed to do was take the sum of squares and divide by the degrees of freedom here. So that's why I left these three alone, and then I changed this one to just that quotient of the sum of squares divided by the degrees of freedom, 1.71. And again, as you can see, that turned out to be correct over here. The next thing you have to do is fix these F values. So these F values, none of them were correct in the original version. And so what I had to do was take the mean square, which was correct, and divide by the mean square within, which was not correct. So now it's correct. So now I just redivide the mean square here by the mean square within to get this F value. And to get this F value, I take the mean square of the columns, the second factor, divided by the within to get the 19.26. And to get this one, I take the mean square of the interaction divided by the mean square within. All of these F's are the mean squares divided by this last one, which we now fixed. So then I got these F values and I typed them in, and you can see that I got all of those correct. Now the last piece that I haven't quite finished with is the p-values. But I got the first p-value to work. Thinking about the F distribution, I'm going to use this command, and you can pause this video and type it into your sheet if you'd like to. It's f.dist, the F distribution, RT, right tail. And I'm going to take the F value with the degrees of freedom, and then the second degrees of freedom is going to be from the error term, the within term. Right? So F distribution with my F, my degrees of freedom, and then the within degrees of freedom. And I got the p-value. Make sure you're entering this one out to 4 decimal places, 0.6077 when you round. And then I got this one correct. So let's now just finish this off by doing these last two p-values and then answering the questions at the bottom of the sheet. So this p-value I'm going to do equals f.dist.rt. The x value is going to be the F. The degrees of freedom is going to be my degrees of freedom, H37. And the degrees of freedom 2 is going to be the degrees of freedom within, and then close parentheses. So that's giving me a p-value of, e to the minus 8 is times 10 to the minus 8. This rounds to 0. This is 0.0000. So let's put that in over here. And you can see we have that one correct now. All right, and finally, I'll do this one. So I'm going to do equals f.dist .rt. I'm going to use my f value, my degrees of freedom value, and then my within degrees of freedom, error degrees of freedom, and I'll get a p-value of 0.0176, 0.0176. All right, and so now I filled out my whole ANOVA table. All that's really left to do is to answer these questions at the bottom. The p-value for factor A is 0.61, 0.61, which is greater than 0.10. And therefore, factor A is not significant. Our p-value is not low. The p-value for factor B is 0. That's less than 0.01. So that is significant. And our p-value for the interaction is 0.0176. It's between 0.01 and 0.025, but in particular, it's less than our alpha value, which is 0.05. So there is interaction, and that interaction is significant. Let's see how I did now. And I think we got everything correct. All right, so I hope this has been helpful. That's how you do problem 6 on your chapter 13 assignment. Talk to you again soon.